What if I told you the ground beneath your feet is not a solid, static surface, but a collection of colossal, slow-moving rafts? And when these rafts grind against each other, the planet itself shudders. Welcome to G Fun Facts Online, and today we're diving deep into the science of seismology, unraveling the mystery of Earth's tremors. So what makes the Earth shake? It all comes down to a concept you might remember from school: plate tectonics. Imagine the Earth's surface, the lithosphere, is a cracked eggshell. These cracked pieces, about 15 major ones, are the tectonic plates. They're not static. They float and drift on the hot, semi-molten mantle below. Where these plates meet, we get action. At convergent boundaries, two plates collide. Think of it like a head-on car crash in ultra-slow motion. This creates massive mountain ranges like the Himalayas, or causes one plate to dive under another in a process called subduction. These subduction zones, like the infamous Ring of Fire around the Pacific, are responsible for the planet's most powerful earthquakes. Then you have divergent boundaries, where plates pull apart. Magma rises from below to fill the gap, creating new crust, like the seam on a baseball running down the middle of the Atlantic Ocean. Earthquakes here are common, but usually weaker. Finally, there are transform boundaries, the real troublemakers in places like California. Here, plates slide horizontally past each other. But the edges aren't smooth. They snag and lock. Stress builds up for years, decades, even centuries, until suddenly the rock breaks, releasing all that stored energy in a violent snap. That snap is an earthquake. This released energy doesn't just stay put. It travels in waves, called seismic waves. Think of dropping a stone in a pond. Seismologists have special instruments called seismographs to listen to these waves. The first to arrive are P waves, or primary waves. They are the fastest, compressing and expanding the rock as they go, just like a sound wave. They can travel through solids, liquids, and gases. A few moments later, the S waves, or secondary waves, arrive. These are shear waves. They shake the ground up and down or side to side, perpendicular to their direction of travel. Crucially, S waves can only travel through solids. The fact that S waves from an earthquake on one side of the planet don't make it to the other side is how we discovered that Earth's outer core is liquid. But the real damage is done by the surface waves. When P and S waves reach the surface, they create love waves and Rayleigh waves. Love waves shake the ground horizontally, which is incredibly destructive to building foundations. Rayleigh waves create a rolling motion, like waves on the ocean. They are slower, but have a much larger amplitude, causing the intense shaking we associate with a major quake. So how do we measure something so immense? We use two types of scales: magnitude and intensity. You've all heard of the Richter scale. Developed in 1935 by Charles Richter, it's a logarithmic scale. This means a magnitude 6 isn't just a little bigger than a 5. The ground shaking is 10 times greater, and the energy released is about 32 times greater. A magnitude 7 is 100 times the shaking of a 5. While iconic, the Richter scale has its limits, especially for very large quakes. Today, scientists prefer the moment magnitude scale. It's a more accurate measure of the total energy released, calculated from the size of the fault that ruptured and how much it slipped. But magnitude only tells you the energy at the source. To describe what it felt like in your town, we use an intensity scale, like the modified Mercalli intensity, or MMI scale. This uses Roman numerals from I, not felt, to 12, catastrophic destruction. An earthquake has only one magnitude, but it can have many different intensity values depending on how far you are from the epicenter and the local geology. Our quest to understand earthquakes began long ago. Often shrouded in myths of angry gods or giant creatures, the shift to science really began after the catastrophic 1755 Lisbon earthquake. It was so devastating it made European thinkers question everything and seek natural causes. The 19th century was pivotal. An Irish engineer named Robert Mallet, the father of modern seismology, literally used explosions to measure how waves travel through the ground. He even coined the terms seismology and epicenter, the point on the surface above the quake's origin. The first real seismograph, an instrument to record the shaking, was built in 1875. By the late 1880s, British scientists in earthquake-prone Japan, led by John Milne, were setting up networks of these devices. A huge breakthrough came in 1889 when a quake in Japan was recorded all the way in Germany. This proved seismic waves travel through the entire planet, opening a window into Earth's deep interior. The 20th century brought us the elastic rebound theory, explaining how stress builds and releases on faults, Richter's famous scale, and Ing Lehmann's discovery of the solid inner core. Later, the Cold War, ironically, helped seismology immensely. The need to detect underground nuclear tests led to the creation of the worldwide standardized seismograph network in the 1960s, giving us an unprecedented global view of Earth's every tremor. This brings us to the Holy Grail. Can we predict earthquakes? The short answer is, not yet. And it's crucial to distinguish between prediction and forecasting. A prediction is specific. A magnitude 7.2 will hit this exact location next Tuesday. A forecast is probabilistic. There is a 60% chance of a magnitude 6.7 or higher earthquake occurring in this region in the next 30 years. Seismologists are getting very good at forecasting, but short-term prediction remains elusive. The processes happen miles deep, under immense pressure, in incredibly complex and varied rock formations. Scientists have looked for precursors, like small foreshocks, ground tilting, changes in groundwater levels, or even radon gas emissions. But here's the problem. Sometimes these things happen and no earthquake follows. And sometimes, a massive earthquake strikes with no warning signs at all. The unreliability means a public warning system based on these precursors would be plagued by false alarms, leading to chaos and public distrust. But now, we have a new tool, artificial intelligence. AI is a game changer for sifting through mountains of seismic data. Machine learning algorithms can detect thousands of tiny microquakes that human analysts would miss, giving us a much higher resolution picture of fault activity. AI is also making earthquake early warning, or EEW, systems faster and more accurate. These systems don't predict the quake, but they detect the first, fastest P waves and send out an alert before the more destructive S waves and surface waves arrive. This can give people anywhere from a few seconds to over a minute of warning. That's enough time to drop, cover, and hold on, for surgeons to stop a delicate procedure, or for automated systems to shut down gas lines and high-speed trains. While not a crystal ball, AI is helping us find subtle patterns in the data that might, one day, lead to more reliable forecasting. The devastation of an earthquake goes far beyond collapsing buildings. Large quakes under the ocean can displace huge volumes of water, creating a tsunami. These waves can travel across oceans and inundate coastlines thousands of miles away. The shaking can also trigger devastating landslides. And there's a bizarre phenomenon called liquefaction. In areas with loose, water-saturated soil, the shaking can cause the ground to temporarily behave like a liquid. Buildings can sink or tilt, and underground pipes can float to the surface. Then there are the fires. Broken gas lines and downed power cables were responsible for most of the destruction in the 1906 San Francisco earthquake. Beyond the physical damage are the crippling socioeconomic and psychological impacts. Recovering and rebuilding can take decades and strain entire nations. So if we can't stop them, what can we do? We build for them. This is the heart of mitigation. Modern building codes in places like Japan and California require earthquake-resistant designs. The goal isn't to make buildings completely rigid, but to make them ductile, able to bend and flex without collapsing. For older buildings, we can perform seismic retrofitting. One amazing technique is base isolation, where the building is put on flexible bearings that act like a suspension system, allowing the ground to shake beneath it while the structure itself moves much less. Other methods involve adding reinforcing shear walls or steel braces. Just as important is land use planning, simply not building critical infrastructure directly on top of active faults or in areas prone to landslides. And finally, there's personal preparedness. Know what to do. Drop, cover, and hold on. Have a disaster plan and an emergency kit. These simple steps save lives. The study of earthquakes is a global effort. Networks span the planet, and international cooperation is key when disaster strikes. And now, you can even be a part of it. The rise of citizen seismology, with affordable personal seismometers, is helping to fill in data gaps around the world. Seismology is a science that is constantly evolving. From ancient myths to artificial intelligence, our journey to understand the restless Earth continues. It's a powerful reminder that we live on a dynamic, breathing planet, and learning to live with its powerful forces is one of humanity's greatest ongoing challenges. Thanks for tuning in to G Fun Facts Online.